And welcome to the presentation of the vehicle dynamics and actuators models as part of the open source model library developed and provided within SetLevel. So let me start from the overview of the architecture of the whole simulation chain as implemented in the simulation use case 2 of SetLevel, where we can see the position and the role of the vehicle dynamics and actuator models and the connections to the other simulation models. So when developing these models here within the project, we defined two main goals. One goal was to develop and provide models with different level of details. The different detail levels are required depending of the specific system under test we have here and on the test specifications. And the other goal was to have model compliant to the simulation standards implemented in the project, which are basically FMI for the model deployment and OSI for the interfaces. So if we have a deeper look here inside this block, we have defined an internal architecture of the vehicle dynamics and actuator models, which is shown here. So we have basically 5 sub-models here. We have the actuator management model. We have the 3 actuator models, which are in detail powertrain, braking, and steering. And we have the vehicle dynamics model, which includes the vehicle body, the suspensions, the tires, and eventually vehicle sensors. So the external interfaces of all this main model are based on OSI, on the standard ASM OSI. And internally, we defined signal interfaces which are based on normal FMI input and output ports. So the definition of the internal architecture and of the single simulation models was done following the current standard ISO 11010. So this is the overview of the finally developed and provided models within the SetLevel project. We have addressed 2 different vehicle types, car and truck, and then we have defined 2 different detail levels, model detail 1, level detail 1 and 2. So we have for the model detail 1, a simplified single model of the car, which is basically a kinematic single track model, and we have also for the truck in a similar way, a simplified single model provided by the partner MAN. And considering the model detail level 2, we have single simulation models for the single subsystems we've shown here before. So we have a single vehicle dynamics model, steering, powertrain, brake, and actuator. And for 2 of them, namely for the steering model and the powertrain, we have 2 different variants. We have a simplified and a complex steering model provided by different partners, and we have for the powertrain an electric variant and a powertrain based on an internal combustion engine. And so the model detail 1 is mostly intended for criticality analysis, such as those carried out in the simulation use case 1 of SetLevel project, and generally for system under test which are not very close or do not have a very close interaction with the vehicle dynamics and actuator models. The model detail level 2 is intended on the other side for system under tests which are closely interacted with the vehicle dynamics and actuators models, like testing the HID function as in the simulation use case 2, or generally for investigating specific vehicle effects such as fault injection, which is presented in the booth B1-3. As main results of this work package, we deliver these models as FMU model library, which is publicly available in this repository. An important topic of this work package was the model deployment, since many developers in this field of the vehicle dynamics and actuator models work with MATLAB Simulink. It was important to define a workflow to generate functional mockup units with OSI interfaces starting from a MATLAB Simulink model. So we challenged this topic with coming up to this workflow, which is depicted here. We start from the development and test within MATLAB Simulink. We implemented the OSI interfaces directly into Simulink with a self-developed so-called OSI wrapper, which is basically a function which translates the Simulink signals to OSI messages. Then we compiled the Simulink models, including OSI interfaces, as functional mockup unit, FMU, using third-party toolboxes such as the FMI kit for Simulink. And then either we compiled the whole block vehicle dynamics and actuators as a single FMU for direct integration into simulation environments such as DSpace or IPG CarMaker, or alternatively, we generate single FMUs of the single submodels. This is single models for braking actuator, for powertrain actuators, vehicle dynamics, and so on. And then we have to integrate them together in specific integration tools using the standard SSP, and then finally provide the combined model to the simulation environments. So this is another important result of the project, which is summarized here. So the workflow to generate FMUs with OSI starting from MATLAB Simulink. Let's move now to the last topic presented here. This is a little bit an in-depth topic, is the validity range observer. So I showed before we developed model with different levels of detail. That means that we have different models which behave differently and which have, of course, different validity ranges. The problem here and the motivation of this part of the work is that remaining within the validity range cannot be guaranteed a priori, especially in closed-loop simulations. So we implement a model, but we don't really know if during the whole closed-loop simulation this model remains within its range, its validity range. So there is the need of monitoring the validity during the simulation in order to ensure results fidelity. And this problem was tackled with a proof of concept implementation of this so-called validity range observer. And basically, the validity range is defined within the model by threshold values of internal states and variables, and the model delivers a validity flag as output, indicating if the validity of the model is within its validity range or not. This is demonstrated here with a simple proof of concept implementation. We have a system under test, which is the motion control connected to the vehicle dynamics and actuators model. And the target of this test here is to check does the lateral position deviation of the car in closed loop with the motion control remains within 0.1 meter. So if the lateral position deviation remains within this limit, the motion control function is validated. Otherwise, we have to say the motion control function is not validated. So the question here is, can I use for this test simulation the model detail 1, or do I need to go to the higher level model detail 2? So the answer depends on the dynamics of the test. In the test case A, we have a test case with a lower dynamic, so we have a maximum lateral acceleration of just 0.2 g. And in this case, the model detail 1 remains within its range. So we see here the results in terms of the lateral position deviations. We have an underestimation of the model detail 1 with respect to the more detailed model detail 2. But this error in the underestimation of the lateral position deviation is negligible and has no effect on the test results, because in both cases the test says, okay, the car remains within a lateral deviation of 0.1. So the motion control can be validated in this case using the model detail 1. But when we move to a test case with a higher dynamics, in this case lateral acceleration of 0.5 g, then we have the problem that the model detail 1 goes outside its range. The lateral acceleration is too high for the assumptions of this model. And we see in the results of the lateral position deviation how the error in the underestimation of this position of model detail 1 with respect to the more detailed model 2 is so high that we would say, if we used model detail 1, we would say here that the motion control function is validated, but instead it is not, because when we use a more detailed model, we see how the poor performance of the motion control leads to a lateral position deviation which is higher than the threshold value of 0.1 meter. So in this case, we need model detail 1, otherwise we are not able to assess this poor performance. So this shows how having this different model, different detail levels of the models need this function of the validity range observer to make the correct choice and have a good results quality. So thank you very much for your attention.